The oxygen nucleus has a radius of 3 femtometers. Part A. With what speed must a proton be fired toward the oxygen nucleus to have a turning point of 1 femtometer from the surface? Assume that the nucleus remains at rest. Okay, well, since the nucleus of the oxygen atom remains at rest, I can find the speed of the proton by conserving mechanical energy. So I have the initial kinetic plus the initial potential equals the final kinetic plus the final potential. So I have, for initial kinetic energy, I have 1/2 times the mass of the proton times its initial velocity squared. There's 0 initial potential energy, there's 0 final kinetic energy, and then there is a final electric potential energy between the proton and the oxygen nucleus, which is K times both of their charges, the product of both of their charges over the smallest distance between them. So the proton is a charge E, the oxygen nucleus has a charge of 8E, so I have, for up top, my product of charges is 8E squared multiplied by the constant K and divided by the radius of 4 femtometers. The radius is 4 femtometers because the radius of the oxygen nucleus is 3 femtometers. The question asks, what is the speed of the proton fired toward the oxygen nucleus to have a turning point of 1 femtometer from the surface? So if my my proton is 1 femtometer from the surface of the oxygen nucleus, and the radius of the oxygen nucleus is 3 femtometers, then the distance between their centers, 1 femtometer from the surface, is 4 femtometers. So that's where I've got my 4 femtometers here. So rearranging and solving for the initial velocity of the proton, I get 2.35 times 10 to the 7 meters per second. So part B, what is the proton's kinetic energy in mega electron volts? Well, the kinetic energy of the proton is 1/2 times the mass of the proton times its velocity squared. Plug in the numbers, and I get 4.61 times 10 to the negative 13 joules. Now simply just convert that to electron volts by this method here, which gives me 2.9 mega electron volts.